In our previous video where we were looking at the Kw and acid-base equilibrium, we explored the concept of the hydronium ion concentration. Because hydronium ion concentrations for most solutions are numbers with negative exponents, these concentrations are more conveniently expressed as pH. So in this video we are going to explore what pH is and use it to determine either the hydronium ion concentration or use the hydronium ion concentration to determine the pH. The pH equals the negative log of the hydronium ion concentration. So the pH scale usually has values that range from 0 to 14. It is used to indicate the acidity of a solution. In the previous video, we saw that a solution is acidic if its hydronium ion concentration is greater than 1 times 10 to the minus 7 molar, and that it is basic if its hydronium ion concentration is less than 1 times 10 to the minus 7 molar. So referencing back to the previous video, we saw that a solution was acidic if its hydronium ion concentration was greater than 1 times 10 to the minus 7 molar, and a solution was basic if the hydronium ion concentration was less than 1 times 10 to the minus 7 molar. Now we can incorporate pH into our definition of an acidic or basic solution. So if a solution has a pH that is less than 7, it is acidic. Neutral is pH 7, and a basic solution has a pH greater than 7. There are two ways to measure the pH of an aqueous solution. One is to use a pH meter, which is more accurate and precise, and the second is to use pH paper that contains an indicator. Alright, let's look at pH paper here. pH paper is made by soaking plain paper with a mixture of pH indicators. A pH indicator is a substance that changes color at a certain pH. When we place a drop of solution on this paper, the paper turns a certain color. To determine the pH, we compare the color of paper with the colors on a chart supplied with the paper. There is the chart. Here in figure C is an example of an indicator. This is an indicator that you can make up in your own home. It comes from red cabbage, and you boil the red cabbage solution. When you have a solution that has an acidic pH, it turns pink. If you have a more basic solution, that is where you can get this change to a yellow color. So you can see, depending upon the pH of the solution, you get a variety of colors. Now let's look at figure A. This is a pH meter which you find in a chemistry lab. We dip the electrode of the pH meter into the solution whose pH is to be measured, and then read the pH on a display. The most commonly used pH meters read pH to the nearest hundredth of a unit. It should be mentioned that the accuracy of a pH meter, like any instrument, depends on correct calibration. So here is a list of the pH of common substances. On the pH scale, values below 7 are acidic, 7 is neutral, and above 7 is basic. So you can see vinegar, lemon juice, they are all examples of acidic solutions. Coca-Cola has phosphoric acid. It is an acidic solution. You have bleach, base, certain detergents. They're much more basic in nature. So let's do a learning check. We need to identify each solution as acidic, basic, or neutral. So HCl with a pH of 1.5 would be acidic. Pancreatic fluid that has a hydronium ion concentration of 1 times 10 to the minus 8. Now, you should know that 1 times 10 to the minus 8 is less than 1 times 10 to the minus 7. So what this means is that this solution will be basic. Sprite has a pH of 3. It is acidic. When you have a pH of 7, you are neutral. We have an OH minus concentration that equals 3 times 10 to the minus 10. Now let's look at this exponent. Right, this exponent is less than 1 times 10 to the minus 7. So what this means, without doing any calculation, that the hydronium ion concentration is going to be greater than 1 times 10 to the minus 7. Remember that Kw equals 1 times 10 to the minus 14, which is the hydronium ion concentration times the concentration of OH minus. Right? So I know just by looking at this, because this is to the minus 10, this absolutely has to be greater than 1 times 10 to the minus 7, so this will be acidic. If you have a hydronium ion concentration that is times 10 to the minus 12, that's less than 1 times 10 to the minus 7, so this will be basic. So when we started discussing pH, I said that the pH equals the negative log of the hydrogen ion concentration. This is a logarithmic scale that corresponds to the hydronium concentration of aqueous solutions. We need to use the negative log base 10 of the hydronium ion concentration. To calculate the pH, the negative powers of 10 in the molar concentrations are converted to positive numbers. So if the hydronium ion concentration is 1 times 10 to the minus 2 molar, the pH equals the negative log of 1 times 10 to the minus 2. Negative times negative, we get a value of 2. For significant figures, to determine the number of significant figures in the pH value, consider the following. The number of decimal places in the pH value is the same as the number of significant figures in the coefficient of the hydronium ion concentration. All right, so let's just look here. We have two significant figures. We have a 1.0, so that's two significant figures. So when we report the pH value, we need to have 2 decimal places. One thing you must remember when you see a pH value is that because pH is a logarithmic scale, an increase or decrease of 1 pH unit means a 10-fold decrease or increase in the hydronium ion concentration. For example, a pH of 3 does not sound very different from a pH of 4. The first, however, means a hydronium ion concentration of 1 times 10 to the minus 3 molar, whereas the second means a hydronium ion concentration of 1 times 10 to the minus 4 molar. The hydronium ion concentration of a pH 3 solution is 10 times the hydronium ion concentration of the pH 4 solution. So let's do a pH calculation. Aspirin, which is acetyl salicylic acid, was the first non-steroidal anti-inflammatory drug, the NSAID, used to alleviate pain and fever. If a solution of aspirin has a hydronium ion concentration of 1.7 times 10 to the minus 3 molar, what is the pH of the solution? All right, I want you to realize that just by looking at this, we should get a pH that is less than 7. 1 times 10 to the minus 3 is much greater than 1 times 10 to the minus 7. So we need to have an acidic solution. So what we are going to do is we are going to say the pH equals the negative log of the hydronium ion concentration. And then we are going to plug in 1.7 times 10 to the minus 3. So our value should be 2.77. And again, we need to have 2 significant figures here because we have 1.7 times 10 to the minus 3. All right, so the next couple of slides, we'll just step you through this in table form. We're given the hydronium ion concentration. We need the pH. We're going to use the pH equation so that we just plug in 1.7 times 10 to the minus 3. Now, this is stepping through how to enter this on your calculator. This will depend upon the type of calculator that you have, so this might not be exact. And you can see your value here of 2.76955, but because we need 2 significant figs, we are going to round to get a value of 2.77. Let's do a learning check. Let's find the pH of a solution with a hydronium ion concentration of 4 times 10 to the 15. Now, before we even plug into the calculator, I want you to realize that this is going to be a basic solution. What this means is that the pH is going to be greater than 7. I know this because the hydronium ion concentration is significantly less than 1 times 10 to the minus 7 molar. Okay, so I've written down what's given. Our concentration is 4.0 times 10 to the minus 15 molar. We need to find the pH. So we are just going to plug in our 4.0 times 10 to the minus 15 molar and take the negative log. So when we plug into the calculator, we'll get 14.3979400. We need to have 2 significant figures, so it's going after the decimal, so it's going to be 14.40. All right, so now that I'm looking at these slides, I see that there was either an error up here or down here. the way the slides proceed is that they are going to use a hydronium ion concentration of 4 times 10 to the minus 5 molar. I want you to be aware that this is significantly different than 10 to the minus 15. If we use 4.0 times 10 to the minus 5, we are going to have an acidic pH, because this is greater than 1.0 times 10 to the minus 7 molar. Alright, so when you plug their value in to the pH equation, again, this is just the calculator display. It might be different for your calculator. Alright, you'll see that you get an acidic pH, and again, you do have to round, so you're rounding to 2 sig figs after the decimal, so it would be 4.40. Alright, so just understand, again, the pH equation is pH equals negative log of the hydronium ion concentration. And if you can understand what these exponents mean with relation to the concentration of H3O plus and OH minus, you're going to be able to predict if your pH is going to be less than or greater than 7. Alright, now what we're going to do is we are going to use the pH to calculate the hydronium ion concentration. So if we are given a pH, we can reverse the concentration and do what is known as the anti-log. On your calculator, it will look like this, a 10 to the x key. So what you're going to do is make sure that you plug in that it's 10 to the negative pH. So let's determine the hydronium ion concentration when we have a pH of either 3.0 or 3.42. So what this means is that our pH equals 3. We are going to do 10 to the negative 3 to get the hydronium ion concentration. Now I said everybody's calculator is going to be different. I know I told you guys not to use your phones, but I'm using my phone because that's what I have readily available to me. For my input, I'm going to put in 3 negative and then hit my 10 to the x. I get a value of 0.001. Now this decimal here indicates, because there's just one decimal place, that our answer needs to be recorded to one significant figure. So we can keep our value written as 0.001 and then just add molar, or we can convert to scientific notation where we have 1 times 10 to the negative 3 molar. Either answer is acceptable because either answer has one significant figure. Let's do B. Alright, here our pH is 3.42. This is going to equal 10 to the negative 3.42. Now, there are 2 decimal places here, so our answer needs to be reported to 2 significant figures. So the calculator says 0.0003819. When we convert to scientific notation, that'll be 3.8 times 10 to the minus 4 molar, my 2 significant figures. So these next couple of slides just step you through the calculation that I wrote down on the previous slide. If you have a value that is a whole number for the pH, the hydronium ion concentration can just be written as 1 times 10 to the negative pH. And so that's what you see here. I did do the calculation out for you. Okay, for 3. This is showing you the inputs that you need when the pH is 3.42 for B. So here you're just seeing what you can put into your calculator. Each calculator is different, so your display might not look like the one that's written here. So again, you have to adjust the significant figures for the coefficient, and you have 3.8 so that you have 2 significant figures. All right, and so here you're just looking at the pH values and the corresponding hydronium ion and hydroxide ion concentrations. Again, when your pH is less than 7, your hydronium ion concentration is greater than 1 times 10 to the minus 7. When your pH is greater than 7, that's where your hydronium ion concentration is less than 1 times 10 to the 7. So keep that in mind when you're doing calculations. The other thing I just want to point out before I end this video is that sometimes you might be given the hydroxide ion concentration. You have a couple of choices here when you're given the hydroxide ion concentration. Okay? The first thing you could do is if given the hydroxide ion concentration, you can just use the kW to find the hydronium ion concentration, and then if you need the pH, you just take the negative log of the hydronium ion. The other option that you have is that there's a value called the POH. The POH is going to be the negative log of the hydroxide concentration. The pH plus the POH equals 14. So just again, another option for you would be, if you are given the hydroxide ion concentration, you can determine the POH. You can then say 14 equals the pH plus the POH and solve for the pH. And then you can just use the pH equals the negative log of the hydronium ion concentration. So you really just need to look to see what you're solving for, but these are the different types of relationships that you can use if you're given the hydroxide ion concentration or the hydronium ion concentration.